managed to connect today. This is the course overview. Over the last 2 days, we had some interesting discussion about AI, large language models, and also what could be coming next. We even talk about finance and politics and trends. And in fact, some of the questions that have been asked yesterday actually it's something that we're also going to talk about today in lecture 3. So some of the slides and contents of lecture 3, actually, we already discussed some of them yesterday. And the past 2 days, instead, the first day we talk about how to represent and classify or cluster data with some basic machine learning techniques. Once again, it doesn't mean that because deep learning is the state of the art, you have to use deep learning all the times. If you have a smaller data set, or you can get good enough accuracy with an SVM, for example, it's totally fine to use SVM instead of a deep neural network. Yesterday we talked about AI, limitations of AI, and also a short introduction to neural networks. And most importantly, how we went from feed-forward neural networks to deep neural networks. So again, this was the first lecture in which we looked at data representation and classification. Yesterday, we talked about different topics in AI, including some conjecture, like the plagiarism conjecture of like if we have all these LLMs generating text, then how long will it take for these LLMs to generate all possible texts? And then this slide was also quite important yesterday. It's important to clarify that although these three terms are used interchangeably, they are not actually synonyms, but a subset of each other. Deep learning is a subset of machine learning, which is a subset of artificial intelligence. So the part of artificial intelligence that we talk about until now is called subsymbolic AI. So that can be like a synonym of machine learning. And in lecture 5, we'll also talk about the other side, the other half, symbolic AI. I'm talking about knowledge graphs, semantic networks, different kinds of knowledge representations. So yesterday we also talked about intelligence. What is intelligence? How can we build intelligence? What are the key limitations of AI? To then discuss about how neural networks work. We had very simple examples on how to build a simple neural network. One important point was also the fact that in order to be able to play and reason around some concepts, we had to kind of translate them into vectors. We had to come up with the vectorial representation. Why? Because neural networks are mathematical models. So this is important to remember for today's lecture, because here we had no choice, but because if we have three types of food, we created the three-dimensional vector. So pizza was 100, burger was 010, sushi was 001, and this is how then we worked with these concepts within the neural network. And the output of the neural network was again one of those vectors that we then translate to the specific concept. So this is also an important concept from lecture 1. We have to kind of shift to a different domain and then go back to the original domain. And this is no different from also how large language model works. They work on embeddings, and then the result is again an embedding that it gets translated into text. So yesterday we also talked about different. Someone has their mic on.
Yeah, microphone.
Shivam.
But please, can you mute others? Maybe. Yeah, please go ahead, Eric.
So, okay, we talk about different kinds of word embeddings, and the ones that everybody is using right now is BERT, and there's many different kinds of BERT in our In our domain, the one that works best is Roberta. In fact, in the latest version of CentiNet 8, we actually compare CentiNet 8 with Roberta. And then we also briefly talk about recurrent neural networks, why they became popular, and also why they became outdated. And the last but not least, we talk about sequence to sequence model, which are also a bit outdated because now most of the tools that we are using are decoder only, but still very interesting from a point of view of meaning, encoding, and decoding. So as we said yesterday in the example of machine translation, these hidden states that are passed from the encoder to the decoder is a sort of Rosetta Stone that encodes, encapsulate the meaning. So yesterday we talked about how very high level how the sequence to sequence models work and how we went from modeling sequences of anything, so of types of food, like in the example of recurrent neural network, to images, to videos, and to texts. That's how we got large language models. And the precursor of large language model, if you remember, it was prompting when we were doing masking to guess what is fill in the blank word in a sentence like this. So from there, then we went into sequence generation, and that's how the generative AI revolution started. Today we have a lot of these models, and we also discussed about DeepSeek yesterday. What's the difference between DeepSeek and ChatGPT, and which one is focusing on which goal? But again, if you have other questions on this, I'm happy to continue talking about it. And last thing we saw was a very brief introduction to transformers. We had some discussions on this, but yeah, here I only put the three key novelties of transformers and some links for those of you who are interested in knowing more about the technicalities and how to build a transformer from scratch. You can look at these video lectures, and then of course you can find a lot of code on Spacey and Hugging Face. So today lecture is really about what to do next. So mostly about the future of AI, but we want to start from also some history of AI. We briefly touch on that, but I still want to discuss about some past failures of AI because nobody tells us that actually there's gonna be another AI winter coming up soon. Actually, many people in finance already talking about some sort of AI bubble. And this is separate from the technicality. So, from the technical point of view, AI is probably just going to improve and become better and better. But then, from a financial point of view, it's not maybe immediate to see some returns because some of these architectures are very costly. And so that's why some are talking about an AI bubble. But before we talk about the future of AI, I want to talk about machine learning in general as a big umbrella that also includes deep learning and many different kinds of learning. So in this picture, you can also see some of those things that we discussed yesterday, like the difference between supervised and unsupervised learning, which again, as discussed, these days is not as clear cut as in the past because then the question is a pre-trained language model supervised or unsupervised? You could say it's both. And then but here the question is, what are we learning in fact? So this actually dates back to the question of what is intelligence, because the way we learn things sometimes is only unilateral. So for example, the way we teach a machine learning model how to reason about something is usually only focusing on one aspect. So to give you an example that maybe you can relate better to, is like if I showed you 1001 videos of snowboarding, then it would be wrong for me to expect that you would be able to know how to snowboard if you've never done that before. I don't know why you guys are so noisy today. Um, so this question is about what is it that we're really learning. So it goes back to the question of what kind of intelligence are we really trying to emulate, and in many cases we are only focusing on one type of task or one type of intelligence. So this maybe relates to the image of the slide of multiple intelligences, where one thing is to know the theory and on one another thing is to know the practice. One thing is IQ, another thing is physical intelligence. And this is important and also relates to back to the of one of the limitations of AI, which is that it depends on the training data. Here is an old example of one of the first driverless cars that killed, took down one of these robots. And why was that? Because in the training data set of the driverless car, there were no robots of this type. It was mostly trained on pedestrian with two legs moving, and this robot didn't have any legs, and so the car simply didn't recognize it. So this again, it's important. It's an important question. What is it that we are learning exactly, and how is the learning happening? And the first principle is that we must not fool ourselves. So it's important to understand the limitations of AI so that we know what are the things that AI can do and the things that the AI can't do. And this is a problem that led us to have those so-called AI winters in the past. And these were mostly happening because there were like a lot of expectations from a general public that then were met. So all these dips or AI winters here happen when basically people thought that AI wasn't working. There were no more research fundings in AI, no more business investment in AI. So this is something that has happened before, and it may happen again in the future. And it could be for a technical reason or for a financial reason. But AI fails are actually a lot in the history of AI. One was something that we mentioned yesterday. Amazon actually was Amazon that was using AI as a recruiting tool, and then later on realized that the AI was using gender as an important feature to shortlist candidates. But then there are many other examples. Lucky these days you don't hear about that anymore, but in the past there were many accidents caused by driverless cars. And this is also an important question of accountability. So in this case, is who is really responsible when accident happens. And last but not least, there was also this hotel, not sure if you heard it, in Japan, that decided to just be run completely by robots, but after a while, um, clients got tired of it because the robots weren't working that well and they just wanted to go back to talking to a real human. There's also this Thai tweets chatbot by Microsoft. I don't know if any of you remembers that. And they just created this chatbot and they put it out there to supposedly learn from the interaction with other users. Initially, everything was very sweet and nice. Things started to go sideways when Thai, which is again a Microsoft chatbot, started to say that the PlayStation by Sony was better than the Xbox. And then things they just went down spiral, like, and they had to literally kill the chatbot and stop the project because the chatbot was becoming increasingly biased and racist. So the problem here is, as we discussed with one of you yesterday, statistics are good when you're working with numbers, but not so much when we're working with text. That's why it's important for us computer scientists to still collaborate and work with linguists. And so the problem here is again that we have to translate text into some sort of numbers, some word embeddings, and then work with those embeddings. But sometimes um, communication language is so much more than that. There could be some hidden meanings, there could be metaphors, there could be sarcasm, there could be some common sense required that it's not in those numbers. And in fact, in general, statistics are a good tool that we use for data analytics and for many things in our civilization, but it's not that you can do everything with stats. For example, if I ask you whether which one of these two here in this image is more scary, many of you would probably say the one on the right, the shark. But the truth is that statistically, coconuts kill more people than sharks every year. But of course, emotionally, we don't feel as scared of the coconut as of the shark. But this is just a simple and funny example to show you why statistics are good in some cases, but not always. Another big issue that we already discussed about some of current AI algorithms that are black box is transparency. So when you have to, if you just care about accuracy and you're working on a toy problem or an application that doesn't involve ethics or human lives, then you don't care. But if you're using AI in the context like healthcare or other situations where you need to know what the AI is doing, then the big question is, do I rather use an AI that is less accurate but with some sort of some degree of transparency or a very accurate AI that does. And this happened a few times already. In this old example, there was this AI that was able to tell better than human doctors which patients was going to die soon, but nobody knows why. There was no way to open this black box to see exactly what was the reason for that. There are other funny examples like Nigel. So today we could say that AI is a bit like this guy, Nigel. This is a Kiwi, a guy from New Zealand who doesn't speak French, but some years ago, I forgot when this was taken, but a few years ago, he won the French Scrabble Championship without knowing French. And so you don't really need to be able to understand or speak the language as long as you are good at sequencing letters and make up words, then it's good enough for you to be considered intelligent or to win a prize. And this is very much what large language models are doing. So we don't have to get confused when we say that at this point we can achieve a high accuracy or human-like accuracy on many NLP tasks. That's not equivalent to say that we have created machines that are as intelligent or even more intelligent than humans. As we discussed yesterday, we are talking about two different kinds of intelligences. Number one is biological and one is artificial. And number two is also about the difference between expert systems and intelligent systems. Most of these models, AI models, are very good at doing just that one thing, and they can't pretty much do anything else. Um, so one thing that we'll discuss also later is the problem of symbol grounding. So um, even when I use word embeddings or simply when I use those vectors that we have fabricated before, the problem here is that it's not true. Like in our brain, it's not like that pizza is represented simply as a vector. You could say that is maybe stored in our brain in the form of some electric signal, but still, it's so much more than just a vector. It's connected to so many memories and of so many facets of the meaning of food like pizza, which entails like how you eat pizza, how it smells, how it tastes, how it looks like, and so on. And this is a problem that is still a problem today. We haven't solved the symbol grounding problem, even for the fastest and smartest large language model existing. They don't really have this meaning grounded. Yes, they can talk about all the different kinds of pizzas, how to make pizza, but they don't really have a representation for pizza. When you ask questions about pizza, they just blurb out an explanation that is maybe generated from documents that answer this question. So, in order for us to have an AI that we can really trust, we also need to look at these aspects. We have to have AIs that are not just playing with numbers and associating concepts with embeddings, but also some sort of representations. That's why, as I mentioned yesterday, we are in my group, we are trying to work on neurosymbolic AI, an AI that is hybrid, an AI that is using large language models together with knowledge representation. But don't worry, we'll talk about this again in lecture 5. Now I want to talk again a bit about large language models. This is the slide that we were already discussing yesterday after one of you asked what's next after large language models. There are many different definitions of large language model. I like this one from Investopedia because it's simple and non-technical, and it focuses on what are the strengths and weaknesses of large language models. So first of all, the definitions say that it's a tool to summarize, translate, predict, and generate. So once again, as I said many times, a large language model is trained, optimized for plausibility. The goal of a large language model is not to give you the absolute truth. It's just to give you an answer that sounds reasonable, that sounds plausible. That's why many people actually got in trouble because they were like there were some legal cases where a lawyer was asking ChatGPT to provide some examples from the past. ChatGPT did so, but then it turned out that these cases never existed. They were just generated. So they sounded very real, they sounded very plausible, but actually they were simply not real. So that's one of the biggest limitations of large language models today. They don't do any fact checking, and that's why people are looking at other systems like bragg system, retrieval augmented generation, or other system that can ground the production, the outputs of large language model into something tangible. And then the second part, in this definition, is that they generate what? They summarize, translate, predict, and generate what? Human sounding text. So once again, plausibility is the goal here. There is no cognitive architecture there. There is no symbol grounding. It's mostly based on data. When there is not enough data available, it hallucinates. So we can talk about hallucination maybe later. It's not necessarily a bad thing. For example, when you talk about computational creativity, hallucination is good because given some missing data, it can generate something completely new based on the little data available. But in cases like question answering, information retrieval, then hallucination is bad because then it's like the system is trying to make up some data that it doesn't have. And last but not least, this was the key point of our discussion yesterday. Their goal is to convey ideas and concepts, or in other words, to give you an answer. And they don't do stuff for you. They don't, first of all, they are not personalized. It's not like they know your personal preferences much. And now some are working on this as well. So now ChatGPT does have some degree of personalization, but still we are far from having a personalized chatbot. And finally, they don't do things for you. And people are already working on this. They call it agentic AI or agentic RAG. But for now, most of the things you see on the market, like ChatGPT And DeepSeek, they just give you an answer and they don't do stuff for you. So this is also related to the example that we gave yesterday when I was talking about like a chatbot. Now every bank has a chatbot. You most of the times you have to talk to a chatbot, but if you ask the chatbot to do something and then a chatbot tells you okay, then you never know whether the chatbot really understood you and really did that thing for you, or is just giving you once again a plausible answer. So this goes back to the concept of the Chinese room argument. It was called Chinese room argument because back in the days, Chinese was still like considered very difficult language, not not as spread out as it is today, and here the conjecture was that if you are a Chinese speaking person, write something and insert it into this box, into this room, and then inside you have someone who doesn't speak Chinese, but he has a sort of rule book in English that tells the person what to blurb out as a reply given the question. So again, like a question answering system. Then even considering assuming that the output is perfectly correct, then the big question is this room, is this system intelligent or not? From the point of view of the user, it is, because you ask a question in Chinese and you get a perfect answer in Chinese. But the truth is that inside there's not really someone that can speak Chinese. So some say that it's still an intelligent system because then the rule book represents the intelligence, and how the rule book is used represent intelligence. But then again, it's just maybe it's just playing around some rules, and it's not we this maybe it's not if we talk about like from a cognitive point of view, I wouldn't define this as true intelligence. And some AI researchers brought this back up. This Chinese room argument actually dates back to the 70s, but someone just brought it back recently in the context of LLMs. So LLMs are extremely good at answering questions, but how can we be sure that they know what they're doing, that they are truly understanding our words? And in this person, Blaise Aguera Icarcas, even went to the extent of comparing LLMs to a person with disabilities and superpowers, in a sense that LLMs, ChatGPT, for example, doesn't have eyes, doesn't have sense of taste. So in that sense, it's disabled because can only see the world through words. But then, yeah, this had a lot of backlash from disabled community. But I don't want to get into that. What's interesting here, the big question here is we use an LLM, it gives us good result. Do we care whether it's truly intelligent or not? And if we even if we care, how can we answer that question? So language, we don't have to forget that the way this large language model works is again on language. So there are, let's not forget, one key point here that we also made here is that they are just language model. They just model language. It's not like they do anything else. They don't take actions for you. And so here also there are some very interesting linguistic theories that we should look at. And some say that actually language affects the way we think about anything, including, for example, for some languages that use feminine and masculine in different objects in different languages can be either feminine or masculine, and depending on that, we have a perception about these concepts that changes based on whether we use them as masculine or feminine. So masculine objects usually are associated with concepts like strength, while feminine about beauty. And we also realized that LLMs have this kind of bias in some of our recent works. We did a lot of this kind of bias comparison with LLM that you can look at if you are interested. But and there are different theories, linguistic theories that say the opposite, that it's thought that affects language. And so different peoples in different parts of the world, they came up with their own language because of the way they thought, because of the things that they did. But so it's important not to forget that language is just it's just a standard, same way as we have different standards in even just in the West to measure things, to measure how long something is, how heavy or how hot or cold something is. Why? Because there is not one unique, general, or universal way to do that. And unfortunately, we don't have many of those universal things. And you could say that maybe mathematics are universal, or musical notes. And there are very few things that are universal. And language is the same as all these different metrics, all these different standards. We had to come up with some sort of way to communicate with each other in a written form, and different people, because they were disconnected from each other when there was no internet, they had to come up with different standards. So it's called natural language processing, because one thing is natural language and one thing is artificial language. So artificial languages are languages that are made up, and including like even programming languages, but better examples could be like Esperanto, or even you, anybody can come up with their own language. There's a study that says that twins usually have, they make up their own language in the first few years of their life, then they tend to forget it later on. But as long as you come up with a shared representation to communicate with someone, then that can be considered a language. But one thing that we don't have to forget is that, for example, a large language model is only working with text, and could be characters, could be letters and sequences of letters and words. But actually, the way that text was actually born was through um, the sound that some words make. Many of the, not all of them, like Chinese characters don't do that, but for example, text and alphabet are there to represent a sound. The combination of different letters of the alphabet are there written so that they can actually replicate a certain sound that we make when we speak. And this is important because then we are actually 2 degrees away working on meaning when it comes to building a large language model. And this is, you can see it also with different languages and how they are, the encoding and decoding of different languages. So, and you can see it in some examples, even in English, where a word actually sounds different from how it's written, or in Chinese, where every character is there for representing a specific sound. That's true, but then um, is done very differently from how the alphabet is combined. And this is also important for those of us, like our group, working on social media analytics, because then when you look at microtext, which is something I will discuss in next lecture, it's also important to be looking at phonetics, because, for example, there's in social media, there's a lot of usage of the number five for different purposes, because in Chinese, the number five is wu, and it replicates, emulates somehow the sound of someone crying when you have a lot of five next to each other. But in Thai, actually, number five is ha, so many ha, one after the other, replicates the opposite emotion of laughing or having fun. And some anthropologists actually say that the fact that we humans, unlike our other species, and even like our um, even as compared to monkeys, and one of the possible reasons why we became so much more different and intelligent um, as compared to them is probably thanks to this FOXP2 gene that allowed us to make different sounds. So in a way, this is actually a very interesting theory that intelligence was, in a sense, enabled by the fact that we could uh, create many more sounds than other animals. So it's a bit like if you think of any animal, there's not many sounds that they can make. And so maybe that was a limitation for them to not evolve into something more intelligent. The fact that they didn't have the possibility to utter more than maybe just a couple of sounds. So this is another thing to take into account. And here I put a funny video that maybe you can watch during the break, which is about how to replicate sound. This is also um, related. For example, if any of you reads comics and you have to replicate or emulate a sound in a comic book, then you have to come up with some sort of code like BAM or some onomatopoeic words that represent that sound. But all of these to state once again that working with text is actually, first of all, text is just a standard, and second, it's just a representation of a sound that we make when we communicate with each other. And then this sound is also then connected in our brain to some sort of knowledge representation. So intrinsically, this is very different from how a large language model works. And in fact, the next slide is exactly about this. Many say that large language models are learn the specific language the same way as we learn a new language. But that's not very much of a fair comparison because, for example, if I'm learning two languages that are very similar in terms of sounds, and there are many of these. So if you take like European languages, like Italian, Spanish, French, they are all very similar. Then it wouldn't be fair to make this comparison, right? So to make the comparison more fair, we could say, okay, maybe it's like us trying to learn a language which doesn't have common phonemes, as a language that sounds completely different from the one that we know. So now the question is, like, for example, if you take one of the three languages that I mentioned before, compared to German, which is very sounding very different, and also the phonemes of the makeup words are completely different from the lemmas and root words of Italian, French, and Spanish. Then now the question is, would this be a fair comparison? And the answer is still no, because then you also have different ways of representing text. For example, Russian uses Cyrillic, Chinese uses different characters. You can have Sanskrit, you can have Japanese characters or Thai. So, okay, let's take a language that doesn't have a common alphabet then. Would it be fair uh, to still have a common structure? So many languages, although they have no common phonemes and no common alphabet, they still have the same structure like subject, verb, and object. And we'll talk about this in the next lecture when we talk about text chunking and other NLP tasks. But then, so we are still not. So we can take, for example, maybe there are some tribal languages that are completely different from the languages that we are used to that don't have this kind of structure. So then would it be a fair comparison of a large language model learning language the same way as we do if you don't have common phonemes, common alphabet, and common structure. Still not a fair comparison, because even if we are learning this weird tribal language that doesn't have a common structure, alphabet, or phonemes, we can still use our common sense as a grounding for anything that I learn from this language. So the only fair comparison would be us trying to learn an alien language, where you have a language that is completely different from ours, so with different structure and no shared common sense. So that's how difficult it would be for a large language model to truly understand meaning and truly learn language the way we do. Then there's much more to talk about, because in fact, as we said, there's really no cognitive architecture behind large language models, but these at least to reason on what it means really to for a large language model to learn and master a language. But nonetheless, many people like to say that they like to make that comparison of large language model learning language as we do, the same as they do for deep learning in general. But that's very far from the truth. This is a nice metaphor, a nice analogy, but it's not true. We do not learn languages like a deep neural network. It's completely different. And a deep neural network learns language in a very bottom-up fashion using training data. And we do learn some of the language like that by example, but not all. There's a lot of stuff that we learn in a top-down manner by using common sense. We'll talk about this in lecture 5, but this is just to say that computer science is full of this kind of analogies and metaphors that are actually, they're nice analogies, but they are not true. They sometimes they are confusing. The same goes with neural networks that we just saw yesterday. It's cool and nice to say that the deep neural networks mimics the structure of the brain, because it kind of looks like the synapses in our brain, but our brain doesn't work like that. Remember yesterday when we took the nodes, the edges, calculated the weights, and used hyperplanes to separate the perception space? That's not how a neuron works. That's not what's happening in our synapses. So it's also important not to get confused here by these analogies. I'll go on and talk about some of the miracles of the brains before I go into talking about the pillars of AI, but I just want to stop a bit to see whether there's any question.
You can unmute a. Hello, Ratnesh. You can unmute others if they have any questions.
So what do you think, Asif? Shall we take a break now or later?
Yeah. Eric, you can take a break. Yeah.
So maybe you guys have time to think about what we talk about and see if you have any question, and also watch this funny video. I hope the link still works. If you guys find any link in the slides that doesn't work, please let me know, especially all those links that I give you at the bottom of each slide. I should have checked it if they still work. But if you do find any link that is broken, please let me know, and I'll try to fix it, like to find the original video or resources. Okay, so shall we take a break now?
Yeah. Eric, we can take a break and then maybe we can start. So by that time, maybe if the participant have any questions, they can think and then maybe they can ask you.
Okay. Okay.
Okay.
Hello. Hello.
Okay, shall we start back? Any questions so far? If you guys also have any questions about previous lectures, that's also fine. And I'm also happy to discuss about anything else. Like if you read some news and you want to discuss about it, is also fine. Like some of you yesterday asked about ChatGPT, DeepSeek, what's gonna happen next. I can give you my opinion. Of course, I don't have the crystal ball to predict the future, and these days it's very difficult to do so. But still, I'm also happy to have this kind of discussions. Maybe not now. Maybe at the end of the lecture. Today's lecture is a bit shorter than other lectures because it's just a glimpse on some of the history of AI and what in brackets the future of AI. In fact, I call it the future of AI just because it's goes after the name of our recent paper, The Seven Pillars for the Future of AI, which is not really a futuristic vision of what AI is going to be, but most like some sort of manifesto, research manifesto, and call for collaboration for any of you who is interested in collaborating with us on one of these topics. So if there's no questions for the first part, we can proceed. So we discuss about how language is just a standard and how there's so much more involved than just a sequence of words and letters. And we also discuss about these nice analogies in computer science that sometimes are a bit misleading. In fact, also when we say that we are emulating human intelligence into machines, we may still actually be light years away from doing that, because even if you take the deepest of the deep neural networks, it's still very far from replicating the neuroplasticity of the brain. We have so many synapses and neurons in the brain that are in the same ballpark of the number of galaxies in the observable universe. So it's we're still far from even just emulating the structure of the brain. We said yesterday that it's a bit like we know the hardware of the brain, but not the software, but still hardware wise, we may still be very far away. And it's not just a matter of how many neurons we have, it's also how efficient the brain is. If you think about it, the brain is relatively small, and it also doesn't consume a lot of energy, unlike maybe some GPUs, and it can do all these in a very efficient manner and very fast and very efficiently. And we are very far from emulating something like that. Now, as discussed yesterday with DeepSeek, we are also looking at this kind of questions. So it's finally, it's no longer just about how accurate an AI model is, but also how efficient, how much energy does it consume, how much space does it require, how many GPUs, how much computing power, and so on. So these are also important questions to be asked in the future, or even now, for those of you who are working on, for example, edge computing or IoT. These are all important questions to ask even now. But so yesterday we briefly talked about this. So the next age of AI supposedly is AGI, artificial general intelligence, where you have an AI that is not just an expert system, but reaches some sort of singularity and can do many things that we do and maybe even better than us. But as we discussed yesterday, this all boils down to how we define intelligence. So if we accept the fact that AI is going to be a disembodied entity that doesn't have any biological traits and hence cannot understand some biological concepts like pain and pleasure, then yes, I can see that we are going to reach that kind of AGI. But when if we talk about an AI that is more intelligent than us in any sort of way, then I don't agree too much on that. Why? Because as we discussed yesterday, we are two different types of intelligences, biological and artificial. But it depends. It really depends on how you look at the problem, because some people, like the late Marvin Minsky in this interview, said that we ourselves are machines, and that sounds a bit silly. But actually, if you think about it, our body does a lot of things in a kind of pre-programmed way. Like many of the bodily functions that we carry out every day to survive are done in a completely automatic manner. It's not like we decide uh, when our heart has to beat, or even if we don't have even control on many of our body parts. So but then who has programmed this machine is been programmed by biological evolution, right? But from this point of view, it's also debatable on what is intelligence, what is a machine, and so on. And some people goes as far to say that we humans, our goal in the universe is just to create AI so that then AI can survive and live for many thousands or millions of years after we'll be gone. Um, and this makes sense in a way, because unless we find a way to colonize other planets at some point, planet Earth, if not because of climate change, when the sun will expand, then humanity will be gone, and supposedly only AI will be left. And AI, in fact, has the potential to even colonize other planets, because it doesn't have our biological limits. So I wouldn't go as far as that into thinking of what is the role of AI and humanity, but nonetheless, maybe this is a good time to be asking some questions, like, for example, if we are building an AI after us, is it even correct for us to build an AI and use ourselves as a model? Are we a good model for an artificial intelligence? And this seems like a stupid question, but actually it's not, because many of the things that we invented are sometimes, yes, um, inspired by nature, but not everything. For example, planes do not flap their wings and still they work. Other things uh, come from the replication of a natural phenomenon, but not all of them. So it's an interesting question um, to think of whether AI needs to be something that reasons like us and has our same beliefs and behaves like us, or it can or must be something completely different. And then for those, especially for those working on affective computing like us, a very important question is, do I want to give an AI the full spectrum of human emotions, or do we want to leave some out? Do we want to have only positive emotions in a, for example, um, in a robot, or only, or the full spectrum? Or do we actually even want to leave emotions out completely? So these are questions that people are asking now, but even Marvin Minsky back in the days asked this kind of question in his book Emotional Intelligence, where one famous quote from him was, the question is not whether an intelligent machine can have emotions, but whether there could be an intelligent machine could really be intelligence without emotion. So this is just to state that IQ and EQ sometimes are very much intertwined, and many of the reasoning and things that we humans do in our daily life, no matter if it's short term or long-term planning, are actually very much tied to emotions. Even the way our memory works is tied to emotions. Another question when we talk about robotics is, how should they look like? And this is also a question that dates back to the 70s. the famous uncanny valley problem, whereby robots that don't really look like humans at all don't cause any problem. But then when you start trying to emulate humans as close as possible, unless you have something very, very good, like for example the Sophia robot, you end up in this valley where people feel very uncomfortable with what they see, because it resembles a bit like a zombie rather than something that you feel comfortable with. And then another important question that even at political level now is being discussed is whether we should have some AI guardrails to limit AI's intelligence, to make sure that actually the AI singularity is never reached. But there are many other questions that some would say like they are a bit philosophical, like if we manage to really build something that is truly intelligent, then how fair would it be to keep it trapped in our server, computer, or phone? So it's an open debate that it's going on in both politics, business, and academia. There's this nice two-page article from IEEE Spectrum from 2 years ago that you can take a look at, and this charts, plots where every major AI scientist is in terms of what they think about AI, and how is highly probable to have AGI, and at the same time that AGI will be dangerous for us. So you see some that they are a very high spectrum, and Geoffrey Hinton is here, and Gary Marcus is here. If you know, Gary Marcus is one who thinks that we still have a lot of things to do before we reach true intelligence. Is a promoter of common sense, knowledge representation, and reasoning. So if you ask me, I would be more in line with what Gary Marcus says. But then it's also true that 1 year after this, Geoffrey Hinton got the Nobel Prize. So maybe we should listen to him. I don't know. Recently, I don't know if you saw the news. There was a debacle between Geoffrey Hinton and Elon Musk. So Geoffrey Hinton tweeted something saying that what Elon Musk is doing is wrong, and now Elon Musk is replying back, and you have kind of the academic community backing Geoffrey Hinton, and on the other side you have all the Elon Musk supporter going against the Nobel Prize. So it's a bit funny to see, and but this just happened. Let's see what will happen next. So, but this is also happening in the business world. Many people think different about what AI is going to do to us, whether it's something good or bad. The truth is that AI is neither good or bad. It's just a very powerful tool, and it all depends on who uses it and how it's used. And this happened many times in the history of humanity with the atom, with genetics, for example. These are very powerful tools that uh, are not either good or evil per se. It only depends on how they are being used. But personally, I don't believe in those apocalyptic scenarios where AI is gonna enslave or kill us all. The real risk that could happen is that we build an AI to solve a real problem, and we give no guardrails, no limit to this AI, and then there could be some sort of unexpected consequences where maybe even we can be harmed by this AI in unexpected ways. And these are the so-called paperclip scenario that were brought up already some years ago, where, for example, you have an AI that is tasked to do as many paper clips as possible and given no limitations, and then it wipes out humanity with the goal of just blindly producing as many paper clips as possible. So you may think this is very stupid. Again, how can something like this happen? It's impossible, right? Actually, it has already happened in some ways with plastics. Plastics were an amazing invention about a century ago, which really helped us to evolve as a society and a civilization, but now it's actually threatening our own existence. And this is because we sometimes it's very hard for us to predict what's going to happen next. When there's something that is looks like only have positive aspects, then maybe down the road, 100 years on the road, can have also unexpected consequences. So that's with all this in mind, we came up with these 7 pillars for the future of AI, which again is not a futuristic vision of what's going to happen next, but more like a research manifesto and call for participation for any of you who wants to work on this. So in the next few slides, I'm just going to briefly describe each of these pillars, and then if you want to discuss more about this, we can discuss it later. If you want to know more details about this, you can also see chapter 1 of the textbook. So the first one is multidisciplinarity. I want to stress this again. After yesterday, we made the example of linguistics. Unfortunately, now with large language models, many computer scientists are becoming a bit obsessed with just having these mathematical models, which are great, achieve high accuracy on many tasks, but still we cannot forget the decades of literature on linguistics. We have to look at other things that go beyond word embeddings and mathematical models to represent language, because once again, statistics are good for numerical data, but for language, we also need something else. So I'm not just talking about linguistics, I'm also talking about semiotics. We'll talk about semiotics later when we talk about symbol grounding, but also psychology. So if you're working like we do in affective computing, instead of just blindly choosing some classes to do emotion categorization, why not reading up some psychological studies on emotions and use or come up with an emotion categorization model that is psychologically inspired? And same with other things that we discussed yesterday in terms of sociology, ethics, and many more. Even now, in education, we are looking at expanding the standard STEM disciplines to also include arts, the arts, and how AI, for example, can be useful for arts, but also arts can be useful for AI. I'm going to talk about this at the very end of this course when I give you some examples of our applications, and one are also in the domain of the arts. The second pillars is actually something that we are going to talk about in details later in the next lecture. Lecture 4 is about the suitcase model. And what is the suitcase model? It's just a framework that contains a lot of NLP tasks. So what's the meaning of this? We'll talk later about some of the benefits of using this framework rather than just focusing on training a neural network with a specific downstream task in mind. But the idea here is that in our mind, there's a lot of tasks that we do almost unconsciously when we try to understand, when we read text, when we hear someone speaking. And it's a mistake to just train a neural network for a specific downstream task, like, for example, polarity detection, and expect this model to automatically be able to handle all the other tasks that we normally can handle. Because if I don't train the model for it, it's a bit risky to assume that it will automatically take care of it. So I'm talking about some of these tasks, like the ones that we can see here in this image, and that we'll talk about later in next lecture, like word sense disambiguation, for example, or metaphor understanding. Many of the things, like also anaphora resolution, it's something that we do almost automatically. We don't have to think twice every time we see a pronoun in a sentence. We can immediately tell what this pronoun stands for, but it's a mistake to assume that a model can just learn all these in an automatic manner. Then, as we will discuss also in the next lecture, having a framework like this not only can increase accuracy but also interpretability, because then if you have different tasks, then you can see which task is doing what, and it becomes so much easier to see where your system is at fault, to do, for example, an ablation study or error analysis on each of these modules. And here, once again, I'm not saying that we have to use all these modules all of the times. It depends on your application and your data. So, for example, if your data doesn't have any sarcastic content, you don't need to do any sarcasm detection. If you're working with formal data, then you don't need a microtext normalization task. I see a question by Vivek. Please ask your question.
Hello, Eric.
Hi.
I just wanted to know, for the point you have written subjectivity detection, do you mean subject detection in the sentence?
Again, this is the next lecture is all about these 15 tasks. And by subjectivity detection, I mean the task of polarity detection to distinguish between subjective versus objective content, where subjective content is all those is opinions. Basically, it's content that is either positive or negative, while objective content is neutral content. And this is, we'll discuss this later. For polarity detection accuracy, is so much better to apply subjectivity detection first and then do polarity detection. Why? Because many classifiers, like for example SVM that we talk about in the first lecture, are binary classifiers that are optimized to classify something as either positive or negative. So if you just use that, and maybe the classifier will be forced to classify something as positive or negative when in fact something is neutral. So yeah, subjectivity detection module is basically just filters out neutral content so that you can focus just on either positive or negative opinions.
Okay. And for the last row, I have one question about that. So,
Which one?
in the last row, pragmatic
Yes.
layer, you
Mm-hmm.
have written aspect extraction.
Mm.
So, from the linguistic perspective, I believe that aspect is like extraction is more like a syntactic task where you have aspect markers and you try to understand what is the nature of the sentence itself. So, how can it be pragmatic?
So thanks for asking this, because then this is also called different ways in different disciplines, because we focus on affective computing. Aspect extraction is more like in a sense of aspect based sentiment analysis. In some cases it also goes under the name of topic modeling. Here the idea is to do a finer grained analysis that doesn't just look at the sentence as a whole, but tries to break it down into some subparts. So these subparts in sentiment analysis are called aspects, but you can also call them features. So you can also call them opinion targets. And you can only do this properly after you've done a lot of other tasks. That's why it's there in the last layer. But this structure is not very strict, in a sense that even the sequence of these tasks is not fixed. It really much depends on the kind of data that you're handling. So this is just a proposed way to do mostly polarity detection, but many other downstream tasks. We also built our chatbot using this kind of framework, and we also then go beyond that by using polarity detection for many other things like depression detection, suicidal ideation detection. But then, yeah, for us, what I mean by aspect extraction is to extract the structure of the sentence in terms of what are the opinion targets, what are the focal points, what are the key words that you need to then do a more finer grained analysis. But we'll talk about this in the next lecture with some examples that also show how aspect extraction is very useful for comparative analysis.
Okay, okay, that will actually help with understanding this thing through example.
Thanks again for your question. Any other question?
Not yet, but I have one question which I will ask after the end of this session.
Okay. Okay, so again, we'll talk about this suitcase model later, and we are here talking about the 7 pillars, and this was just the second one. So first is multidisciplinarity. Again, very important for us AI enthusiasts not to forget that we also have to take into account other disciplines. Task decomposition, again, don't it's good to use neural networks and just throw as much data as possible to learn a specific downstream task, but sometimes it's better to do task decomposition to look at each of these tasks separately. Parallel analogy is also a very interesting topic that was once again proposed by the late Marvin Minsky. And it's very interesting in a sense that I think today it's really something that we need. So once again, as AI experts, or as engineers in general, we tend to be a bit too obsessed with optimization. So when we are building an AI model, we want to pick the best representation, the best set of parameters, the best model, and so on. But sometimes maybe it's better to have even the same data represented in different formats instead of just picking the best. Why? Because then if you have a dynamic system that can shift from a representation to another, then you have a much more robust and flexible model that can maybe switch representation when problem solving starts to fail, a bit like we humans do when we want to like look at the problem from a different point of view. So this is something that we are also doing for effective computing tasks, and I think is something to be taken into account. Symbol grounding is something that I mentioned many times during the previous lectures, and it's the central pillar, not by chance, and that's because it's something that we really believed on in terms of uh, like what is one of the biggest limitations of current AI that needs to be fixed or at least mitigate. And so this comes from the field of semiotics, and this is also something that we're going to talk about a bit more in detail in lecture 5 when we talk about neurosymbolic AI and common sense knowledge representation and reasoning. But here is a preview of that. This means grounding words and meanings somewhere. So this is something that we just discussed before the break. So if I take a verb like generate in a large language model is just associated to an embedding. I don't have a meaningful representation that tells me what generate actually is. Yes, I can ask ChatGPT to give me an explanation. Yes, I can get hundreds different synonyms of generate, but what really generate is a different question, because then once again a large language model given a question is just going to generate an answer for you, but that's not how we reason. We try to really visualize what's happening. So having a sort of grounding that tells me that, for example, generating X means that I go from the current state of affair of the operating environment where X doesn't exist to a new state where X now exists can be very useful for doing, for example, spatial reasoning. And then on top of this, I can build a lot of other um, types of meanings and concepts. But here, the most important concept is that in order for me to have something, a model that is, I wouldn't say truly intelligent, but at least cognitive inspired. Words, it's good that words are associated to embeddings, but they should also be linked to some sort of explanation or meaning encoding and decoding so that the meaning of having these specific set of letters coming one after another is actually grounded somewhere. And the power of this is that once you have a representation like this that is language agnostic, actually supposedly it's valid for all existing languages, because languages once again are just a standard. So why not try to build some sort of universal symbolism that can, on top of which then we can use all languages. Similarity measure is also very important. We discussed this when we were talking about Euclidean distance and cosine similarity in lecture one, if you remember. And today, even people that are building better and better AI models, when it comes to doing classification or calculating similarity between the data points, they actually still using either Euclidean distance or cosine similarity, mostly cosine similarity for the reasons that we explained in lecture one. But then recently, some people are correctly pointing out that cosine similarity may not be as good as we thought. And there's this famous paper published in WWW conference by Netflix that basically shows that cosine similarity, at least for their data, doesn't really work. So it works for very simple problems. In general, cosine similarity, don't get me wrong, it's a very good way to calculate the similarity between any kind of data, but it's not always working perfectly. So for Netflix, which is maybe slightly different, it's not exactly a classification problem. The one that they have is more about a recommender system, so maybe closer to clustering. But for them, as shown in this paper that you can read, is not very good. And actually, that's also our claim in CenticNet 7, for example. 2 years ago, we came up with a different way of calculating similarity in a vector space. Why? Because when you talk about similarity, cosine similarity, you're actually trying to look at the angle between two vectors like we discussed. But sometimes these two data points could be in two completely different manifolds of the space. So the space is not just a set of points. The points tend to organize themselves into manifolds. And sometimes you could have 2 points that, from a Euclidean point of view, are very near to each other, but they belong to two different manifolds. And so looking at the pure similarity without taking into account the topology of the space could actually be a mistake. So we are working on different ways of calculating this topology aware similarity. If you are interested, we can discuss more later, or you can take a look at our paper CenticNet 7 from 2 years ago, actually 2022. Another thing to mention here is that, once again, when we talk about cosine similarity, we tend to think that that's the only similarity, like a semantic similarity. But then there could be also other different similarities at play. So one example in our field, affective computing, is that if you have two data points, two concepts like happiness and sadness, from a semantic point of view, maybe they are actually very similar because they are both emotions, But then from an affective point of view, they are completely different. So um, they should be in completely different areas of the vector space. So that's exactly why we came up with an affective version of a vector space model, affective space, which focuses more on these nuances rather than looking at the more general semantic similarity. Another important pillar is intention awareness, which in general means creating a model of the user, like doing a bit of user profiling so that um, you don't just give general answers in the case of question answering, but you can actually cater to the specific preferences of the user. So I'm going to talk about this a bit later when I give you some examples of how we do this in our group. But here is another short paper published last year in which we talk about all the some of the possible different degrees of personalization that you can apply to basically have a better human-computer interaction. So even when you talk about sentiment analysis, if you just have some personality detection there, then you can have you can better understand whether a piece of text is positive or negative depending on the personality of the user. And here you also have subjectivity, which is different from subjectivity detection that we mentioned before. Here, subjectivity means knowing basically the personal preferences of the user. So if you get to know from some user data or metadata, for example, that they love pizza and they are allergic to shrimp, and the next time when even just you write, you see a sentence like my dad brought me to eat shrimp, it's neutral actually, because it doesn't contain any positive or negative information, but knowing the personal preference of the user, you know that that's actually negative. And finally, trust. How to define trust between even two humans. It can be tricky. That's why we also have to look at other social sciences to define and to have a good definition of trust, because trust actually is very similar to those other words like intelligence that we understand more or less what it means. But when you have to define it in a way that you can build it from scratch, then it's a bit tricky. But here in this pillar and in this short paper, or in this also short video that you can watch later, we discuss about trust specifically in the context of recommender system. And here, actually, the question is really important. Like, we use recommender systems much more than we realize. Like, so many of the products that we use, like Netflix, but even things like, I don't know, dating apps, they are all recommender systems. And here the question is, who tells me that the next item, person, book, video, restaurant that is being recommended to me is really for my own best benefit? Maybe it's actually following the business model of the company. So how do we know? How do we know about that? We need more transparency. We need to be able to trust our recommender systems by, for example, being able to see or ask how they came up with this the next recommended item. And once again, this seems like a trivial question, but it's not so trivial, because in some cases, like for example dating apps, the business model and your goals are exactly the opposite. Maybe you go on a dating app to find your life partner, but and so to get off the dating app as soon as possible, but then that's not the business model of the dating app, who wants to keep you there for as long as possible. So these are important questions to ask. And in this paper, we also talk about many other interesting things, like the fact that this over reliance on recommender system and AI may actually uh, cause humanity to have um, simpler and more rare interaction among each other, because then here the question is, if I have I don't know if you watched the movie Her, but if you have some sort of recommender system that you can really talk to, and it replies back in a very natural manner, and it knows you so well that can give you the best possible recommendations, then what's the point of even having any interaction with other human beings? So that's another kind of philosophical questions that we can also discuss later if you are interested in this kind of topics. So this concludes actually this lecture, and I'm happy to take any questions. So I don't, it's a bit difficult to do a course like this online. Like last time I was at IIT Patna, I can see the faces of you guys, and I know whether you're getting excited, bored, or whatnot. So this course, maybe
Yeah.
last time the course was a bit more technical, so there were more um, it was a bit more hands-on. This time I thought it's better to do something a bit more high level, and then you have the tutorials to do something a bit more hands-on. And for those of you who are more interested in the details, you can go and read the textbook, or look at some other of more technical short videos that we have on our channel. But then I'm also happy to hear any sort of feedback in terms of, like, if this is what you expected, if this is useful for you, and if you would like to be more technical next time. I don't have time now to change the slides. We only have 2 lectures left, but I'm always happy to get this kind of feedback. I'm doing this a bit high level because I think that's what you need. And now in the business world and also in academia, it's relatively easy to find like code on Hugging Face or Spacey, but then it's more important, I think, to have a bigger vision and understanding of what are the limitations and strengths of AI, so that you know what to do next in your specific field. So that's why I'm teaching this course this way, and that's also how recently I've been teaching to my students in the university. Of course, at the university we have more time, and we are also doing more practical things, more tutorials, more assignments, and more hands-on experiences. But it's actually very similar to what I'm doing here in this course, maybe in a bit more condensed manner.
Eric, I have a question for pillar number 4. If you can move to that slide.
Sure.
I'm going to ask you some basic questions related to that. And
Please.
because this kind of intrigued me in a very different way. Uh, so if I see logic definitions, first, my question is it really possible to logically define each and every entity of a language?
No. This is something that people have tried in many ways. The very first attempt to do this was Psych by Doug Lennart. And then recently, you also have also efforts by linguists like Bliss Symbolics was an interesting project as well. And Shang also came up with the concept of semantic primitives. So I'm not saying that we have to do this for every word in every language. Probably it's not possible to do that, especially for abstract concepts. But starting to build something like this for a specific application or a specific domain, like we are doing for effective computing, can be useful later on to build something on top of this. So this here I do it with logic, but I'm not saying that it must be done with logic. What I would like to have in the future maybe is some sort of visualization tool that makes, for example, an LLM imagine things as it's reasoning, like visualize a certain scenario, a certain situation. This once again would only work for very tangible objects and not for abstract concepts. But then, yes, to answer your question, it's not feasible and possibly impossible to create this kind of logic definition for every word. In fact, what we did here in CentiGNet 7 and CentiGNet 8 was to mostly focus on just verb concepts and only those that are polar. So either a positive or negative concepts, because then for other concepts that are more neutral or more abstract, sometimes it's very difficult to come up with a logic definition for them.
But I see defining through a very explicit boundary of positive and negative, then there is a problem. Let's say I want to logically define a predicate or a word. Let's say ungenerate. How do you define that?
Ungenerate,
Yeah,
you mean the opposite of generate,
yeah. So how would you treat that?
as this as the opposite state that goes from X existing to not existing.
But it don't you think it is more like a case of saying that um, so suppose if I take an example of boy and girl, okay, and somehow I believe that girl is an opposite property than the boy. But then if someone comes up and he defines unboy, means unmaking of a boy, it's not a girl, but it's not a boy either. So
Yeah,
I think how if I treat ungenerate as an equivalent of that, so I'm not
it's
considering
true.
it as
Yeah.
an terminate thing.
It's a very good point that you're making. I can't think of a specific example, but there is actually a way to define this in logic. So there is the opposite or the negation is one thing, and then the complement is another. So, for example, I get your point. Like generating something, the opposite of generating. The question is the opposite of generating something is doing nothing or terminating something. So this is something that you can still define in logic, and but then yeah, we have to be able to make this kind of differences. And in many cases, like you said, it's not true that everything is black and white. For those, maybe you want to be using fuzzy logic instead of a more binary classification. So I hear you. There are many things that require that for which like standard first order logic is not enough or is not good. But again, this is more about an attempt, an example of how we can and should try to mitigate, if not solve, the symbol grounding problem.
Okay, so in case if I for my hypothesis I take, okay, it's possible to define things on a black and white term. Forcefully I think of that, okay. So in that case, suppose I wish to define a predicate which may be like um, self-containment, and it's a mix of generation and termination. And I wish to use these tools which you have written over here, that there is not x implies some x, and if there is an x implies not x. So how would you join them, or how would you add them, sum them, in order to define the predicate like self-containment?
I don't know. We have to come up with some ways to define things that are more complex. What we do in sentiment analysis context is also to define a time dimension. So, for example, um, when you have like the primitive barter exchanging like a double transfer of ownership, but then depending on what you're exchanging and for how long the meaning change. So you have to combine different primitives and think of way to also include the time dimension, because the same primitive like barter exchanging of A for B takes different names in English. If one of the items that you're exchanging is money, then you can have buy or sell. If you keep it for a limited period of time, then it becomes lending or borrowing something. Or if you take it against someone will, then you're stealing from someone. That the exchange, like the primitive is the same. It's an exchange of objects, or getting an object from someone or something, but then you have to add on some other representation that can specify maybe with the time dimension, or some sort of like willingness of the other party to give you or not this object, to then specify what it means. Here, what we're trying to do definitely ultimately is to have to take this top-down approach where we find a way to represent a specific meaning, and then from there we go on and see how many how many words in English or in any other language correspond to this kind of transfer in different contexts. So again, I'm not saying that we can do this for all words. For some will be impossible, for some will be more complex. We'll have to come up with different techniques to do this, but I think we should try at least. Given a simple set of primitives and a specific domain, I think this is doable and can result in maybe a new learning or reasoning paradigm that can then later on be adapted to bigger problems.
Okay, and one last question related to this. I'm sorry, I'm taking much of your time.
Oh no, we are here. We still have another 10 minutes, so no problem.
Okay, so suppose again I further make a subset. Okay, these are some properties, and these are the things I can define in a black and white thing. So where do you sit this small set of work uh, to be working or to be producing good result in a scenario of LLM? Where do you think this is fitting actually?
Yeah, that's also a very good question, and I'm gonna talk about it in lecture 5. So, but we also mentioned that yesterday. You can have a hybrid model where you still use an LLM, like we use our intuition for fast reply, and then you can have another system. So this is also called in cognitive psychology system 1 and system 2, where you have a framework like this one that can verify facts, that can do different kinds of reasoning, like common sense reasoning, because then you don't really need to have this representation for maybe some basic question answering task. But if I start telling you a story, or you have to understand a scene where a specific object is moving between different hands and people are moving around, and then you have to understand where this object is, and then maybe you need a kind of reasoning like this. So I'm not saying that we have to come up with this representation and use it for everything. I'm saying together with LLM, you should also have another, maybe more than one ways of reasoning, and we should have a system that is able to switch not just among different representations like we saw here, but also a switch among different ways of thinking.
Okay, thanks a lot. That was really insightful.
No problem, my pleasure. I see there's another question by Palash.
Yeah, hi Eric.
Hi.
So I don't have a question per se, but I need your insightful comments on something that we are doing right now.
Sure.
So I don't know whether you are aware of the Bhashini initiative of Government of India or not. So under that initiative, the government is planning to build MT systems or MT technology for Indian languages, uh, covering all the 22 scheduled Indian languages and apart from that, other regional languages as well. So what approach we are following right now is developing the parallel corpora from Hindi to Indian languages and then training the MT systems based upon that. So, I mean, what is your take on this approach and what is your feedback and what more you would like to add in this?
Yeah, thanks for telling me about this project. I didn't know about it and I want to know more because actually here in Singapore, we are doing something very similar for Southeast Asian languages. So I'm collaborating with this institute called AI Singapore, and we are building large language models for Southeast Asian languages. The models are actually open source. It's called Sea Lion. Sea Lion stands for Southeast Asian Languages in One Network. So Sea Lion, you can Google that or you can ask me for the link, and you can take inspiration from that for your work. In general, I think it's very good to have that because then our experience in other Southeast Asian countries is that every country has different problems, and you really need a model for each of those. But I think one thing that it's also missing from there is the thing that we just discussed here. We should also have, on top of these large language models, also other sorts of symbolic AI or knowledge representation that, for example, can understand the different cultural nuances between different Asian countries or different regions of India, so that, for example, you have one large language model that is more nuanced towards the specific beliefs or foods or ways of thinking of people from that specific region, because that's the only way you can really do personalization. So this is also related to the thing that I was mentioning in terms of intention awareness. And unless you build a large language model for each of these facets, you also need, in any case, you also need some other model or framework that can help you understand all these nuances. So once again, I would have, if possible, I would have some sort of system one, system two framework that, yes, uses a large language model trained on location specific data, but also a knowledge representation or a knowledge base, even something as simple as an ontology that tells you what are the specific cultural or even religion or other kinds of differences between these different user groups, basically. But yeah, tell me more later. Maybe you can have discussion separately or send me an email. I want to know more
Yeah,
about this project, and I can
sure,
also tell you more about Sea Lion.
sure, definitely. Yeah, we'll connect.
Okay, I think it's time to stop here. You guys probably have the tutorial next. If there's no more questions, then I would say
Pro-
yes.
Prof- Professor, are you
Yes.
going to talk about ethics in AI anywhere in your lecture?
ethics. No, not really.
So maybe in the future lecture, if you can talk about the research scenarios, I mean, just small discussion about
Okay.
what is the idea of ethics when we talk about AI
Mm.
ethics.
Yeah, thanks. I will. That's a good suggestion. I can add more material on that next time. The only thing that is near to ethics is this concept of the responsible recommender systems, but definitely there could be more that can be discussed in terms of ethics, because again, it's one of the disciplines that I also added here in the first pillar. But then you're right, I don't talk much about ethics in this workshop. So yeah, thanks for the advice. Okay, I guess I'll say goodbye now and enjoy the tutorials. And if you have more questions, you can ask me tomorrow. So see you guys tomorrow at the same time for lecture 4.
Thank you.
Bye bye.
Bye bye. Thank you.